Okay, so let's talk about percent composition. Well, if sometimes you're already provided a breakdown of all the elements, and if that's the case, you can kind of skip down to step 6. But if you haven't already been provided a breakdown, you have to do your own breakdown, which are the same steps as to finding your molar mass of a compound. So your first step is to separate compounds into elements. Your second step is to determine the moles of an element. Your third step is to determine molar mass of elements. Your fourth step is to multiply moles times molar mass of the element to get your total grams of that element. And your fifth is to add up all grams of elements for new molar mass. Once you have all 5 done, this is your breakdown. Then you do number 6 for each element in a compound, which is total grams of the element. You divide it by your molar mass, and then you multiply by 100 to get your percent of that element in the compound. Now, a lot of times these percent compositions are your starting points for your empirical formulas. So this is a good introduction to empirical formulas, which we'll be doing today. Okay, let's do an example. Let's do calcium carbonate. So it's CaCO3. Now remember the first step, and we're going to make a little table with this. And if you follow along on the table, you're going to make your life so much easier. So it's calcium carbonate. So we're going to do Ca over here because that's our first element. And remember, the big letters separate your different elements. We have C, and then we have O. Remember, our second step is to determine our moles of each element. So we do that by looking at the compound. We have calcium written once. There's no subscripts, so we can have 1 mole calcium. Now, when you're doing any kind of percent composition, as much as I like to write really big, please make sure you're writing smaller so you leave room for some of your extra work. For carbon, we're looking up here. It's 1 mole carbon because, again, no subscripts. And then oxygen, there's this 3 attached to the oxygen. That means there's 3 moles of oxygen because any kind of subscripts means the amount of moles. So you have 3 mole oxygen. Now keep in mind, I'm making sure that I'm writing down not just units, but what those units belong to, so that I can ensure that when I am going back and double checking my work, I understand what I'm doing. So make sure that you're putting, I like to really separate all of my columns by these lines. It makes me visually see the different steps of my equation. It also lets me easily go back through and check if I'm making mistakes. Math mistakes are often easy if you don't, 1, check your units, and 2, if you round too early. A lot of people want to round over here. You should only round at the last part of it. The next step is to determine the molar mass of the elements. We're pulling those right off the periodic table. I realize different periodic tables have different amounts of elements, or that is also true, but I was going to say molar masses because different periodic tables round differently. I will make sure they're all standardized for assessments. So the one I used today had at 40.078 grams per mole of calcium. We had 12.0107 grams per mole of carbon, and I had 15.9998 grams per mole of oxygen. Now, you got to make sure you're adding your items up. Now, when you're multiplying across, remember your dimensional analysis. The moles cancel out, so you end up with grams of that unit. So, 1 mole calcium times anything is going to be that same thing. So 1 times 40 gives me 40.078 grams of calcium. That's supposed to be a small a. So for every 1 mole of calcium carbonate, I have this many grams of calcium. I end up with 12.0107 grams of carbon, and I end up with 47.994 grams of oxygen. So you're just multiplying across. I'm going to add another row here, and then what I'm going to do is you're going to add all of these up to get my total grams for every 1 mole of calcium carbonate. This is your molar mass. So I end up with 100.0 0.0827 grams per mole of calcium carbonate. I always box my molar mass because that's often part of a final answer, and then that helps me confirm what we're doing next. And what we're doing next is our percent composition. So you take the number of grams here, you divide it by this number, and then you multiply it by 100 in order to get your molar mass. So what we have is 40.078 divided by 100.0827, all multiplied by 100 will give me 40.04% calcium. We have 12.0107 divided by 100.0827 gives me something to the effect of 12.00% carbon. And I should, based on this 52, I should have something right around 48% oxygen. If I don't, I've done something somewhat wrong, but if I get right around 48%, that's an easy way of checking because your percentages have to add up to 100, right? 47.994 divided by 100.08 gives me right about 47.95%, which I'm kind of right on where I expect it to be. You can write it like this. There's another way of writing it, which is another way you may see. So these are all your percents. You might write it like this, which is calcium, carbon, oxygen. You write it in the order that they show here, and that would be 40.04%, 12.00%, and 47.95%. If you ever see it listed in this format, it goes in order. So the first percentage goes with the first item listed, the second percent goes with the second item listed, and the third percent goes with the third item listed. Okay, let's talk about empirical formulas. Empirical formulas are the lowest ratio of elements in a formula. So, what we often see are molecular formulas. So when you're seeing like C2H4, C4H6, CH3, I'm making these up, CaNO32, those are all molecular formulas. An empirical formula is the lowest ratio of elements in a formula. So one empirical formula may spawn or have hundreds of molecular formulas that could be tied to it, because it's the lowest ratio of elements. So there's two ways to solve. If you're given a formula, you just simplify it into the lowest ratio of elements. But oftentimes you're given a percent composition and then told to find the empirical formula. Or you're given a percent composition and told to find the molecular formula. Either way of those questions, you have to find the empirical formula first, and that is what I'm here to tell you about. So let's look at how to do some just simplifications. So let's say we have C6H12. We can simplify that to CH2. If we have C3H12, we can simplify that to CH4. If we have H2O2, we can simplify that to HO. So just always a simplification. Okay. So to find the empirical formula given a compound, or the percent composition, not a compound, you're going to do this nice 7-step process, which is a lot easier than it actually lists out, and I'm going to walk you all through it, okay? So the first thing is to list each percent in the element. I do it working in tandem, so I make my rows of each element in percent. You're going to change your percent to gram. You're going to find the molar mass of each element. Again, that is on the periodic table. We are loving the molar masses right now. You're going to find moles of element by dividing your grams by your molar mass to get your moles. So if you're working down, you'll be setting up all of your equations. You're going to divide by the lowest mole. That makes sure that that lowest mole is at least, the lowest ratio is always a 1. But you're going to divide all by that. So sometimes you have these really easy round numbers, like you get around 0.1, 0.2. You can round it to the nearest whole. You get like that 0.3, 0.4, 0.5, 0.6, 0.7. It's not as easily roundable. So we say is you try multiplying it all by 2. If it gets easily roundable numbers, those are the numbers you use. Sometimes you have to multiply all by 3, but you always start with 2, and then you write your formula. It'll make so much more sense when I give you an example. Because once I get to give most people an example, it's like, oh wait, I totally see it now. So, okay. Given calcium, this, because you will often get a setup like this. So often you'll get something like, what is the empirical formula of this compound given these percentages? Like, that's a legit setup. Like, I didn't write it all out, but it'll be like, what is the empirical formula given the percent composition of this compound? So remember, your first step is to list the percent in each element. Now, please, when I say I list them in columns, I really do. So remember, this calcium goes with this 40, so I go 40.04% calcium. Then we have 12% carbon. Now, I know this is, 2 decimals. Again, I'm trying to write it smaller because I'm trying to keep it in my paper. And we have 47.95% oxygen. My columns are a little wonky. I apologize. But then we do the magic change. You guys ready? The next one is to change percent to grams. Okay. 40.04 grams of calcium. 12 grams of carbon, and 47.95 grams of oxygen. Because it's out of 100, and they're all like can relate to 100, we can literally just take the percent sign and go, boom, grams. Makes life a lot easier if you're doing with grams. Then what you do is you find the molar mass of each element. And so we could look it up on your periodic table. And so it is 40.078 grams per mole of calcium. It is 12.01 grams grams per mole. I put the mole, I remembered, and it is 15, let's just do 16 grams per mole oxygen. I'm changing it up a little bit just for the sake of my paper to make my life easier. Under this problem, go ahead and write, if you're doing the setup that I'm doing, you write a line underneath, and then you remember you're dividing down. So if you do 40.04 divided by, no, I cannot do my calculator today, divided by 40.078, you end up with 0.999. At this point in time, do not round because you don't want to round prematurely. 12.01, 12 divided by 12.01 gives you 0.999, and 47.95 divided by 16 gives us 2.99. And these, if you're going to be really specific, which we should be, this is mole calcium, mole carbon, mole oxygen. Then again, you choose your lowest mole and you divide by it. Yeah, but they're both the same, 0.999. So you would just divide by 0.999. And this is not, you're not putting moles of anything, you're just dividing by the number. 0.999 divide by 0.999. And we end up with 1 mole calcium. We end up with 1 mole carbon. And we end up with 2.99 mole oxygen. Because it's 0.99, we can just round that to 3 mole of oxygen. So if we're looking at rounding, this is our final number. This is a 1 mole calcium rounded, 1 mole carbon. I'm just color coding to make sure that people can follow. And then 3 mole oxygen. And then you write the formula. And these are your moles in your formula. So we end up with CaCO3. Okay, let's talk about molecular formulas and how to find them from an empirical formula. So remember, your molecular formulas are the official formula of a compound. You must be provided an empirical formula or a way of finding the empirical formula. So if you're given a percent composition, you have to find the empirical formula first before finding molecular formula. And you must be provided the molecular molar mass in order to find the molecular formula. So, again, we're going back to molar masses. Everything's about molar mass. So, given an empirical formula of CH2, what is the molecular formula of a compound with a molar mass of 220.05 grams per mole? Do we have a molecular formula? Check. It could have been said, given an element with percent composition, you were given a way to find the empirical formula, so you would have been able to do it. Then, are you given molar mass? Check, so you can move forward. So your first step is to always write down your empirical formula. So my empirical formula is CH2. Boom, done. My next step is to find the molar mass of my empirical formula. So I go back to those 5 steps of the molar mass. First step, separate your elements. Second step, write your moles per element. 1 mole C, 2 mole H. Our third step is to write the molar mass of each element as on the periodic table. So we have 12.01 grams per mole C. We have 1.008 grams per mole H. Then we have, you multiply across. So we end up with 1 times 12 is 12.01 grams C, and we end up with 4.016 grams H. You add them together down. So we end up with 14.026 grams per mole CH2. Once you have the molar mass of your empirical formula and you have your molar mass of your molecular, you can find your N. So you got to solve for N, which is just a fancy way of saying N equals molecular molar mass over your empirical molar mass. Please don't ask me why they call it N. They just wanted to make things super fun and interesting. So our molecular molar mass is what you pull from the problem. That is 350.65. Don't worry about units so much here because you're just trying to get the N. And you're going to divide that by the one that you got, which is 14.026. And if you get an N that's at least roundable, you round. It's not always 100% perfect due to, like, you know, errors or differences in periodic tables, but it should be pretty close. So 350.65 divided by 14.026 gives me 25. And then you take this N and you multiply it by your empirical formula. So this 25, and you multiply it by your empirical formula. So I'm going to be multiplying it by CH2. And you just multiply across. So 25 times C gives me C25. 25 times 2 gives me 50, H50. And that is my final molecular formula.